The very last thing or the part of transmission electron microscopy is the screen or CCD camera. So image system in transmission electron microscopy consists of either the phosphorus screen, which may be made of fine 10 to 100 micrometer particulate zinc sulfide for direct observation by the operator or by the CCD camera. So after CCD camera, the image is enhanced and transmitted electronically toward the screen that you have either the LCD or LED where you can see the object of interest. The electron beam, after passing through the projector lens, it strikes the phosphorus screen, and then user is able to see the image of object of interest. The image formation can also be seen by CCD camera on your LCD or LED screen. As an example, on the bottom left hand side, you can see the image formation by transmission electron microscopy of ZNO crystals. So in this image, there are a few crystals of varying size and all of the crystal of ZNO. For example, this one is a bigger crystal of ZNO, it's a medium ZNO crystal, and the bottom there is small crystal, and on the top there are much smaller crystals. But all of the crystals are made of same material. So this is a single crystal, this is a single crystal, this is a single crystal, and the top they are of single crystals, but of varying size. If you critically observe, then you will see that in each crystal there is a variation in the gray tone. For example, in this bigger crystal at the bottom there is much darker region, or it resembles to a black color. On the top it's a medium gray color. In the middle region, especially here, it's a whitish gray color. A very similar observation can be made for the top small crystal. Although the material is same and it is single crystal ZNO, but here the color is blackish or dark gray color, whereas the bottom or the tail is whitish gray color. So the million-dollar question will be, why there is a variation in the same crystal which are of the same material, ZNO? Why? Because there is a variation in the density. For example, at the bottom there is a dark area. It means the number of atoms are more and they are densely occupied in this area. Here the number of atoms are relatively less with respect to this dense area, and in this lighter region the number of atoms of ZNO are much less with respect to all other region. If the density is high, the area will be dark color. If the density is low, the area will be of light or whitish gray color. This is because if the density is high, then the electron beam will feel hindrance to pass through the sample at this region. If there are less number of atoms, for example here, then the beam can easily pass through. If the beam can easily pass through, then means in this region the image form here on the CCD camera or the phosphorus screen, more number of electron will strike. If more number of electron will strike, the area will appear the area will appear in the as it's a brighter region. If less number of electron appears on the screen, then the area will be dense. If more number of electron appear on the screen, then the area will be, or the region will be, whitish gray. And the same philosophy is applicable to nearly all of the transmission electron image formation. If you have an image formation of any of the object by transmission electron microscopy, and if there is a variation in the gray tone, then you can infer that the dark area are of the dense area and the light area are less dense area with respect to the dark area. So by varying density in the same material, you will observe variation in the grayish tone. The sample preparation in case of transmission electron microscopy is very much difficult because we need a very thin sample, such a thin that the electron beam can pass through. If electron beam is not passing through the material, then you will have no image at all. So to prepare sample for transmission electron microscopy, there are three common techniques. Sample can be prepared by spark cutter or focus ion beam or mechanical and argon ion milling. But care has to be taken so that plastic deformation shall not be happen. If there is a plastic deformation in the sample, then there will be unwanted structural defects on the microstructure level. And these unwanted structural defects can be easily visualized in transmission electron images. In case of spark cutter, you have an electrode in the form of wire and you cut a material surface such that few particles are removed from the surface, and these few particles will act as a specimen in transmission electron microscopy. So what is actually happening there? The electric discharge between a wire and the specimen is used to cut the material by removing very small particles, as I earlier mentioned. And these small particles are from the surface of specimen only. So you cannot go through the bulk material. If you go through the bulk material, then the material will be in the form of chunk. And the chunk material are not eligible as a specimen in transmission electron microscopy. So the limitation of transmission electron microscopy is you need a very thin particles. If there is a thin particle, then the ion beam can pass through. If there is a big chunk, no, you cannot get anything. So only a small particle from the surface of material will be removed by an electrode, and these small particles will act as a specimen. Second technique is the focused ion beam. So in case of focused ion beam, what is happening? A thin slice of sample will be cut by the ion beam on the scanning ion microscope. So the main advantage of this type of method is that this method allows for selective thinning at desired location. So where you want to cut material in a very thin slice, just move the ion beam at that area, and as this is happening in the scanning ion microscope, so you can easily move the ion beam to your selected area. So just move your ion beam to selected area, take the ion beam, and then a thin slice will be cut at the desired area. And even you can move layer by layer material on the very same location just to investigate what is happening in the bulk. But at that time you will have many samples. For example, surface layer will be cut, then the below surface layer, and then more on, and each layer will act as a separate sample in transmission electron microscopy.